Hi, my name is Nicole, and today we're going to talk about part of kinetics, which is the study of reaction rates. In particular, we're going to look at what can we do to influence how fast a reaction rate happens. The learning objective that we're using today comes from a combination of an NGSS standard and a Texas standard called the TEAC. We'll look at those at the end. But as far as what you want to be able to do by the time we finish this video, you want to be able to identify what the conditions are that can speed up or change the rate of a reaction and explain how those work using something called collision theory. The first thing we'll take a look at is, hey, let's explore what you already know because you have some experiences with some of these things already. You might have tried to dissolve sugar in tea, which is easier to do in some situations than others. If you've ever used a glow stick or had a glow bracelet or necklace, your parents might have told you, hey, if you put that in the freezer, it'll last longer. Or maybe you've even done the amazing and wonderful baking soda volcano, either built a volcano itself or maybe just actually put baking soda and vinegar together in the kitchen and watched all the bubbles do all the fun things. I'm going to show you two experiments today, really simple ones. The first one being making sugar dissolve. So we're going to have some constants and some variables, just like we do in any experiment. We're going to keep the amount of water the same and the amount of sugar the same in the same container. We're going to do one experiment that checks on how does changing the temperature of the water change the ability for the sugar to dissolve, and then how does stirring change the ability for it to dissolve. So let's take a look at what happens. The first thing I want you to look at is we have four sets of conditions here. We have warm and cool water being stirred and not stirred. So take a moment to think about, of the four sets of conditions, which one do you think will make it dissolve the fastest? Then I want you to go ahead and try to rank them from what you think will be the slowest to dissolve all the way up to the fastest to dissolve. Take a moment to pause the video and go ahead and write down your hypothesis. Go on when you're ready. Okay, so we have four videos on here. Even though the sugar doesn't go in at exactly the same time, you can get a general idea of what's going on. The ones that are being stirred are on the left. The ones that are not being stirred are on the right. I want to draw your attention to the third video, the warm water plus sugar, and see how it looks kind of cloudy and then it sort of settles out. If you look at it really carefully, you can actually see everything kind of swirling around in there on its own. It's almost like it's stirring itself. And then you take a look at the two videos on the left, and you can definitely see that the sugar in the warm water and being stirred dissolved way faster than anything else. And then we're almost to the point where the cool water being stirred dissolved. And then the warm water by itself, there's still some sugar left, but it's slowly going away. And then the cool water without being stirred still has quite a bit of sugar in it. Did anything surprise you about what you saw? Was your hypothesis correct, or do you need to make a change? The second experiment we're going to look at is what happens when we react baking soda and vinegar. In this case, the amount of baking soda, the amount of vinegar, and the container will be the same. And then we're going to again do two experiments. One is going to be the same as the last time, so this is almost like a second trial. Warm vinegar versus cool vinegar, so changing the temperature. And then the second experiment, instead of stirring, this time we're going to test does changing the concentration matter. 5% vinegar is what comes out of the bottle just straight away. And then 1.25% vinegar, what I did was I took 1 part regular vinegar and then I put 3 more parts water in it. So that diluted it by 1/4. So this time, instead of getting the fastest set of conditions, pick what you think are going to be the slowest set of conditions. And think about what you learned in the last experiment that might tell you this would be so. Okay, so I split these up. This time we have warm versus cool vinegar. You're going to look for the amount of bubbling, how fast the bubbles happen, how high the bubbles go. So in this case, what we saw is that warm vinegar, the bubbles get really high and big and then they dissipate really, really quickly, which indicates that the reaction is happening faster than it did in the cool reaction. Now we look at the two different concentrations. Again, we're looking for a reaction where it bubbles up really fast and then dies down quickly. Okay, and in this one, you can see in the 5% vinegar that it bubbles up pretty quickly and it dies down quickly, but it actually reacts for longer. And I think in this case, it's happening because we're actually running out of acetic acid, which is the important part in vinegar that makes this reaction happen. Okay, so we've looked at warmth makes things go faster, stirring makes things go faster, and higher concentrations makes things go faster. So what happens with this is it all comes down to something called collision theory, which is as easy as it sounds, things smash into each other. So collision theory just means that the atoms are actually traveling around in the container, bumping into walls, bumping into each other. When you have a collision between the particles, if it's just perfect, then a chemical reaction can happen. So reaction rate depends on the number of effective collisions, and the more effective collisions you have, the faster the reaction will go. So there's two things you have to have effective collisions. You have to have the correct orientation. So if you have two things that hit each other side by side, but they're not supposed to react that way, they're supposed to react head on, they won't react. So you have to have the correct orientation, and you also have to have enough energy. You have to have enough energy to be able to overcome the activation energy. So if we look at this little diagram over here, the activation energy is the amount of energy that's required to reach the transition state, which is the highest energy state. So every reaction takes a little bit of a bump to get going. If the energy in the system is too low, there won't be enough energy for any of the particles to react. So to have an effective collision, you have to have both the correct angle and enough energy. Okay, so let's take a look at what that looks like on the particle level. This particular example is going to show you the correct orientation, but a very low energy. The low energy is indicated by this little temperature thing right here being pretty low, so that's showing it's at a low temperature. And with a low energy collision, you won't get a reaction. This awesome FET simulation, same thing. You have the correct components, and now we have plenty of energy because the temperature is way up high, but it's shot at an angle. And so when the two particles collided, they didn't collide in the right orientation. So even though it's high energy, if it has the wrong orientation or the wrong angle, it won't react. And then, of course, our third example being the reaction that works. So you can see here that there's enough energy to make the yellow and pink attach and then reverse back to each other. So finally, effective collisions happen when you have the correct orientation or angle and sufficient energy to overcome the activation energy. We've kind of already talked about this. How do we create a faster reaction rate? But we're going to look at it in terms of the collisions themselves at this point. When you stir, we saw that stirring created a faster reaction rate. In terms of collision theory, what we have happening here is we are sort of mechanically speeding up the reaction. We're stirring and we're moving the particles around and we're making them bounce into each other. We're not really increasing the kinetic energy, we're not really increasing the temperature, but we are mechanically making the particles bump into each other more often, which then means that they're going to have a greater opportunity to hit at the right angle. And then the ones that have enough energy will go ahead and react. The second thing we did was warming the solution. So when you increase the temperature, you're also increasing the kinetic energy. So if you have a low temperature, the particles are moving slowly. When you increase the temperature, the kinetic energy goes up and the particles move much faster. Okay? So in collision theory, what we're looking for here is two things to happen. Number one, if the particles are moving faster, then they're actually going to bump into things more often just by the fact that they're moving more quickly. The second thing is you'll have more particles that have enough energy to overcome that activation energy hump. If we take a look at this, this is a little particle model here. You can see that the temperatures are different. This is a low temperature. This is a higher temperature. So you can see that in these two examples, here we only had one particle that was able to react. Here we had 4 particles that were able to react at the higher temperature. So there were more particles in the mixture that were able to overcome the activation energy. The last thing we want to look at here, or I guess the third thing we want to look at here, is when we change the concentration. We saw with the vinegar that the 5% reacted a whole lot faster than the 1.25%. And again, this kind of goes back to collision theory. If you think about it, think about having 5 kindergartners in the gym playing tag. There's plenty of space for them to move around. They're going to try to get to each other, but they may or may not make it. They're probably not going to run into each other. They're not going to run into the walls. What if we take that same gym and we put 100 kindergartners in it? At that point, there's kids everywhere. They're running all over the place. They're bumping into each other. They're tripping each other. They're bouncing off the walls. They just hit each other more often. So because of the fact that they hit each other more often, you're more likely statistically to get more effective collisions, which then will increase your rate. So again, here's another visual of this. You have a low concentration on the left where there is one particle that was able to react. And then you have a much higher concentration on the right where there were several more particles able to react. We are making the assumption here that they are at the same temperature so that you have an even distribution of energy. Okay, the last one we didn't look at is taking a look at surface area. So I'm really grateful to Carleton University's Chemistry Roadshow for this. And what this guy is doing is he's showing you the effect of surface area. What he just did was put something called lycopodium powder in his hand. Lycopodium powder is extremely flammable, so whatever you do, don't try this at home. But he showed you that by putting a little pile of it in his hand and just lighting that match, all it did was make a little singe into the pile of powder. However, if we change the surface area by blowing it out into the atmosphere, it's like kind of like flour, you can see that he's able to get a much stronger reaction. He gets an explosion, for lack of a better description. So what we see is that the greater the surface area is, the more spread out and small the particles are, the higher the reaction rate will be. In terms of collision theory, what that looks like is it's an access issue. If you have a big block of something, you can only get to the edges of the big block. Everything in the middle is protected from being reacted. If you break all of those up, like in the picture on the right, you can get to more surfaces of the material, which means you have more places for collisions to happen, which means you're going to have more effective collisions. Okay. The last thing I want to look at here is just to say thank you very much for taking the time to listen, and I hope you learned a little bit about what affects the rate of reaction and collision theory. The standards this was based on was NGSS Performance Standard HSPS1-5, which relates to using collision theory to explain why reaction rates can be changed by agitation, warming, and concentration changes. And then Texas Essential Knowledge and Skills, which similarly asks you to investigate and explain how changing temperature, agitation, and surface area influences the rate of reaction. Finally, I'd like to say thank you to the University of Colorado Boulder for their PhET simulations. They do such a fantastic job of letting us see the things that we cannot see in chemistry because they're so hard to explain and impossible for us to see. I'd also like to thank the Carleton University Chemistry Magic Show for the use of their video there from YouTube. It is a great description of how changing the surface area really works. And then everything else in here was either made by me or was found through a Google search where the copyright is allowing reuse with modification. Thanks very much. Hope you learned something. Ask me questions in the comments below if you'd like.